Okay, these are the notes for 11.7. These take a while, so I'm going to move pretty quickly. Anytime I say pause, work through it yourself. You're going to want to do that because I'm going to be jumping right back in with the answers pretty quickly. So on the first one, we have two rectangles, and I asked you to find the scale factor, the ratio of the perimeters, and the ratio of the areas. So please push pause now, work those out, and make sure to simplify your ratios. Okay, as you see, I worked out the scale factor to be 1 to 2, the ratio of the perimeters to be 1 to 2, and the ratio of the areas to be, you could have said 1 to 4 or 4 to 1. Okay, so what I notice here is the scale factor and the perimeters are the same, and it looks like the ratio of the areas is pretty similar, but not the same. Okay, we're going to do that one more time. If you have the printout of the notes, you're going to need to add in the 12 root 2 and the 4 root 2 part. And again, I'd like you to find the scale factor, the ratio of the perimeters, and the ratio of the areas. So please push pause and work through that now. All right, I have those answers here. And again, I see the scale factor was 3 to 1 and the ratio of the perimeters was a 3 to 1. So I see that those were the same. And then I see the ratio of the areas was 9 to 1. So I have 3 to 1, 3 to 1, 9 to 1. And back here I had 1 to 2, or you could say 2 to 1, 2 to 1, 4 to 1. So think about that relationship. All right, now the next two pieces are just looking at ratios areas a little differently. These are two triangles that have the same height but not necessarily similar. So I drew a picture here for you. So the black triangle and the blue triangle, you see they both have the height here, but they have different bases. So if you set that up, okay, the area of the black triangle over the area of the blue triangle, the 1/2 will divide into 1. The heights divide into 1. So basically, when you're doing the ratio of the areas, you're just finding the ratio of the bases when they share the same height. Notice that I did not say that these were similar triangles. They're not. It's just that they share the same height. So if the two triangles share the same height, the ratio of their areas is equal to the ratio of the bases because, again, the heights and the 1/2 will divide to be 1. So there's the important part right there. Now, if we have two triangles with the same base, what is the ratio of their areas? So again, I drew a triangle for you here. You can see they both share the same base here, but the blue triangle and black triangle have different heights. So once again, when I set up their area formulas, they have the same base, their heights were different. So the 1/2 divide to be 1, the bases divide to be 1, and I'm left with the ratio of the heights. So when two triangles share the same base, and again, I did not say they were similar, the ratio of the areas is equal to the ratio of the heights. All right, so we have a lot of information there. The next slide is just going to go through talking about that similarity we started with. When you saw the scale factor was A to B, what was the ratio of the perimeters? Okay, and hopefully you're saying A to B because it was the same. Now for the ratios, again, I'm hoping that you saw a relationship there. Remember, it was 1 to 2, 1 to 2, 4 to 1, 3 to 1, 3 to 1, 9 to 1. So the ratio, if the figures are similar, the ratio of the areas is always going to be the square of the scale factor. And you can kind of remember that in, for example, if you're measuring sides in, let's say, inches, perimeter would also be in inches. So that would be an A to B, and area would be inches squared. So you square it. And now we're going to work through some practice problems. Okay, again, I'm going to ask you to try to work through these the best you can. And then I will come back and tell you the answer. So please push pause now and work through it as best you can. All right, for the first set, I have the triangles outlined here in blue and green. I know that these angles right here are congruent because it's a trapezoid and the sides were parallel, so alternate interior angles are congruent with parallel lines. The same applies here. So by AA similarity, I know the green triangle and blue triangle are similar. So the ratio of the areas is equal to the scale factor and I should say squared there. Okay, so it'd be 3 squared to 5 squared. Okay, and that equals 9 to 25. Not 35, 25. So I can prove these are similar. Now, what I put in here in red is not important for this problem, but it will be later. I just need you to remind you again that blue and green triangles we proved are similar. That means that all of their sides reduce to a 3 to 5 ratio. I don't know what they are. I just know the ratio of this side to this side should reduce to 3 to 5 because the triangles are similar. And corresponding sides in similar triangles are proportional. And again, this side and this side should reduce to a 3 to 5 ratio. So I put 3x to 5x, 3y to 5y. Again, I don't know exactly what those numbers are, but I know that the ratio of them is 3 to 5 because the triangles are similar. For the next triangles, I put them in blue and green. If I look at the altitude dropped from D, because that's the common vertex, you'll see both of them share that as a height. If you remember from some of the quiz review and things you did, the altitude of a triangle sometimes can come outside of the triangle like it did here in the blue. So in this case, and you'll see I have the 3x and 5x from the previous slide carried over, they share the same height. And then the ratio of the areas is equal to the ratio of the bases. Because again, if you set this up and called this the height, the 1/2 in the heights would divide out to be 1, and you would be left with a 5 to 3. 3x to 5x, which reduces to a 5 to 3. Okay, in the next one, this is probably the trickiest one of all. I have the blue and the green triangles here. They both share the same base of AB. So the ratio of the areas is the ratio of the heights. Now here's where I really need to try and help out. The 3h and 5h are the heights of those similar triangles. And if you look, I have the height of the green triangle here. That is also the same as that segment. Okay? So the height of the blue triangle is, we can call it 5h. The height of the green triangle is 3h plus 5h, or 8h. See how that kind of, not that part, sorry. That's 3. No, not that part. So I found out this height is 8. Again, 5 plus 3. And then the height of this one is 5. So that reduces to a 5 to 8 ratio. And that's a tricky one, so you might need to think through that one a little more. Over here, I have 2 problems for you I'd like you to try. So focus on what the triangles are. When you're looking at the triangles or the shapes, first thing you ask, can I prove they're similar? Okay, if you can't prove they're similar, then don't worry about the a squared to b squared type ratios. Then look, do they have a common base? Do they have a common height? So there's a problem here, you could push pause, and there's a problem here. Again, looking for the same thing, the ratio of the areas. So push pause now and try these problems. All right, sorry I'm moving quickly. I don't want this video to be too long. So when I outline the triangles in blue and in green, what I saw is I'm not really sure if I can prove that they're similar. I don't have another angle here or anything. So I'm going to prove, I did see they had the same height, BD. So the ratio of the areas, if they have the same height, is equal to the ratio of the bases. The base of the green triangle is 3. The base of the blue triangle that this height is drawn to is 15, 3 plus 12. That reduces to a 1 to 5 ratio. Over here, again, I outlined the triangles in blue and in green. I decided to use that they had the same height of BD. So the ratio of the areas equals the ratio of the bases. Again, that BD height is drawn to this side, 4 in the blue triangle, 9 here. So the ratio of the areas equals the ratio of the bases, which is 4 to 9. In the next slide, ratio of the corresponding heights of 2 similar triangles is 3 to 5. That means this is your A to B ratio. What is the ratio of the corresponding sides? Well, this is the scale factor, and the scale factor is the same for the sides, so that is also going to be 3 to 5. Okay, what is the ratio of the perimeters? Well, the ratio of the perimeters is the same as the scale factor, so that is also 3 to 5. And then the ratio of the areas is not the scale factor, it's the scale factor squared. So that gives me a 9 to 25 ratio. Okay, I have 4 true or false statements. Again, I would like you to try these on your own and then come back. So please push pause, try them out. All right, in the first one, if two quadrilaterals are similar, that's important. Then their areas must be in the same ratio as the ratio of the perimeters. Okay, as the square of the ratio of the perimeters. So you would square the ratio of the perimeters. The ratio of perimeters is the same as your scale factor. If the ratio of the areas of two equilateral triangles, if these are equilateral, I know they're similar by AA similarity. If that's the ratio of their areas, that's the a squared to b squared ratio. The ratio of the perimeters is going to be the square root of that. So that is true. The next one is false because we aren't sure that the rectangles are similar. Not every set of rectangles are similar. They'll have the angles the same, but the sides may not be in the same ratio. And in number 4, it is true. Squares all have the same sides, so we can prove all squares are similar. All right, circles also all similar to each other. So what is the ratio of their circumferences and the ratio of their areas? And again, here's a pentagon problem. You can push pause and try these out yourself and then come back. So push pause now. Okay, for this one, diameters is a ratio of 10 to 9, so that's their scale factor. The ratio of the circumferences is going to be the same as that, 10 to 9, kind of like perimeters. And the ratio of the areas is going to be squaring the scale factor, so 10 squared to 9 squared. In this one, the first thing I did was look at the ratio of the areas, 96 to 24. I simplified that ratio to 4 to 1 and said, okay, and that is important. I would simplify that first down to the lowest terms. 4 to 1 is the a squared to b squared ratio. This means the scale factor is 2 to 1, square root both. The perimeter of the first pentagon is 40. Add all the sides together. So a to b equals perimeter of first to the perimeter of the second. Okay, so the scale factor was 2 to 1. The perimeter of the first was 40 over the perimeter of the second, which we don't know. Solve that proportion, and you should have gotten 20 centimeters as your answer. What's very important here is you recognize when you need a squared to b squared and when you need a to b. I wanted perimeters, so I made sure that when I did the perimeter ratio, I was setting it to the a to b ratio, not the a squared to b squared. Be very careful with that. Okay, that concludes the 11-7 notes.